All right, today we're going to decode a hidden language. It's one that powers pretty much our entire world, from the GPS in your car to the very structure of the internet itself.
Think about it for a second. You pull out your phone, you're stuck in traffic, and in moments, it figures out the absolute fastest way to get you home through this insane web of streets. How on earth does it do that?
Or, hey, try this puzzle. Imagine you need to connect a whole town with new telephone lines. You've got dozens of houses, countless ways to connect them, and every single connection has a different cost. So how do you find that one perfect layout that connects everybody for the absolute minimum price?
Now, these two problems, they seem totally different, right? One's about speed, the other is all about cost. But it turns out the solution to both comes from translating them into a really simple, universal language, basically a map of dots and lines.
So let's learn the basic vocabulary of this language. Now, it's technically called graph theory, but don't worry, don't let the name scare you off. It's actually incredibly simple and intuitive.
Okay, so at its heart, a graph is really just a way of drawing relationships. You've got your key locations, we call them vertices or nodes, those are just the dots. And then you've got the connections between them, we call those edges, and those are the lines. That's it, that's the whole foundation.
And with just those two simple ideas, we can start describing really complex networks. So a path is just what it sounds like. It's a walk along the lines from one dot to another. And a cycle? Well, that's a path that forms a loop. It brings you right back where you started.
And that idea of a cycle, a loop, is absolutely critical. See, to solve that telephone puzzle, we need a special kind of graph we call a tree. A tree connects everything, but it follows one super important rule. There are absolutely no cycles, no loops. Because a cycle would mean you've got a redundant, unnecessary connection, and we're trying to save money here.
All right, so let's use that idea and tackle our first big challenge, building a network for the lowest possible cost. So here's the setup. Each dot you see is a house, and each line is a potential telephone connection, with a number representing its installation cost. The goal is to connect every single house, one way or another, while spending the least amount of cash possible.
Now, the method for solving this it's beautifully simple. It's called an algorithm, which is really just a fancy word for a recipe. Here's what you do. First, you just look at all the possible connections and what they cost. Then, you just pick the cheapest one available. You add it to your network, but, and this is the most important part, you can't add it if it creates a loop. Then you just keep doing that over and over until everyone's connected.
Let's watch it in action. The algorithm just goes down the list, always picking the cheapest option. It grabs the edge that costs 2, then the one that costs 3, then the one that costs 4. But look, see what happens when it gets to edge BC? If we added that line, it would create a loop between points that are already connected to each other. That's a cycle, so it gets rejected. The algorithm just says nope, skips it, and moves on to the next one.
And by following that super simple recipe, always pick the cheapest line that doesn't form a loop, we eventually find the one single best solution. The absolute minimum cost to connect every single house is 30.
What we've just built here has a name. It's called a minimum spanning tree. It spans the network because it connects every single point. It's a tree because it has 0 wasteful cycles. And it's minimum because, well, its total cost is the lowest you can possibly get. It's the most efficient network imaginable.
Okay, so now let's switch gears. We're going to go from cost to speed. We're moving from building a network to navigating one. So here's our second puzzle. This is a map of a park. The letters are different locations, and the numbers on the lines, that's the time it takes to travel between them. Our mission is to get from the entrance, that's A, to the main attraction, T, as fast as we possibly can.
To solve this, we use something called Dijkstra's algorithm. The way it works is really cool. It starts at our starting point, A, and it kind of explores outwards like a ripple in a pond. It figures out the time to reach its immediate neighbors, and then it permanently locks in the shortest path to the closest one. Then, it uses that point as its new base camp to explore its neighbors, and it's constantly updating its map until it's found the absolute fastest route to every single spot.
So this table shows you how the algorithm builds out its solution, locking in the fastest path to each destination one by one. And check out the final result, the quickest way to get from A to T. It's not the most direct route you might think. It's actually this kind of winding path from A to B, then to E, then to D, and finally to T.
And here's the key takeaway. The total travel time for that path is 13. Any other route that might look more direct would actually be slower, and the algorithm has mathematically proven it.
This is precisely the logic that's running under the hood in your map app every single day.
Okay, now for a really fascinating twist. What if, instead of trying to find the shortest path, we wanted to find the absolute longest one?
I mean, this is what is so powerful and elegant about this way of thinking. If we take our shortest path algorithm and we just make one tiny little change, we swap the word minimum for maximum, we suddenly solve a completely different and totally critical real-world problem.
So why on earth would you ever want to find the longest path? Well, in project management, this is a huge deal. It's called the critical path. It represents the sequence of tasks that are all dependent on each other and that take the longest time to finish. That path tells you the absolute bare minimum time your entire project is going to take. Any delay on any one of those tasks on the critical path and the whole project gets delayed.
So as you can see, this hidden language isn't just for solving fun little puzzles. It is a fundamental tool that is actively shaping our modern world in countless ways. This language of networks, it's literally everywhere. It's guiding your car with GPS. It's routing this very data to you across the internet right now. It's being used to design efficient power grids and even to analyze our social networks. And, as we just saw, it's the key to keeping massive, complex projects on schedule.
And this really brings us to a final thought. This way of thinking, of simplifying immense complexity down to just dots and lines, it's an unbelievably powerful tool. It really just leaves you with a question. What other seemingly impossible problems are out there right now, just waiting for someone to see them as the right kind of graph?